okay? Okay, concerning the original lecture date, so this is an exception today because for some other reasons I had to be absent from Erlangen and could not make it this morning, so we shifted it to this date. So usually we have our lecture on Thursday in the let me phrase it in this way, in the first slot. And my proposal is, and I think you will all agree, that we start at 8:30. Is this okay? Yeah, later is not possible because then we will not make it up till 10. But we have this possibility, and I think, okay. So from next week on, 8:30 in Übungsraum 3. So, okay. I will do something I will do something in this lecture which I usually not do. I totally deviate from the description of the module, because this description of the module, at least from my point of view, is far too ambitious, and also does not 100% fit with this level you have reached meanwhile. So there are much more up to the research topics up to the research line. So maybe this is something you can do in the third and fourth master semester. And did we do something more basic? So I have decided to, as I said already, a little bit to identify a few subjects we would like to cover. So the first subject, where we know already something about it, but not about the analysis of it. So the first subject will be time-dependent PDEs. We have seen those models already, so we have seen all the time-dependent Navier-Stokes equation, of course also time-dependent Stokes equation. If we go down then to the energy conservation, we have the heat equation, and more general versions, we have the diffusion equation. So this is one class, so the second order equations, second order in space equations we want to deal with. And then of course there's this other class. There is the first order in space equation, the Euler equations, the wave equations, and so on. And okay, the wave equations does not come in the form of a second order in space, but a second order in time, first order in space, but second order in time, second order in space, but can be rewritten, as we have seen, as a system of first order equations. So the aim of this first section is to look at procedures to show existence of solutions for those linear problems. So first we are still in the realm of linear problems, which makes the world much simpler. Then as a second part, we will see how far we will come there. Based on that, to some extent, as I said, we will look at the Navier-Stokes, not fully of course, and the Euler equations. So here and then, of course, the problems become more pronounced. We have systems, we have nonlinear equations. And then this is, so to speak, the first block, dealing with time-dependent equations, and the second block going back to stationary equations, but now really looking at the nonlinearity. So the key word would be nonlinear elasticity. So we have touched this a little bit in the sense that we have derived such models with hyperelastic material, for example, but we haven't said anything. Sorry. This is number 4. This is now the application. So we start with number 3. So maybe you have heard already this keyword. So what we have to do a little bit is we have to do a little bit calculus of variations. So what does that mean? We have seen that a stationary problem can be written either in the PDE form or in the form minimize an energy. And of course, we can tackle both forms, asking ourselves something about the equations. For example, the existence of a solution. So we can either say, okay, let's go down to the most simple equation, the Poisson equation. We can either look at the Poisson equation directly at the weak form, say, okay, this is a bilinear form. What do we know? Lax-Milgram. Can we check the assumptions and so on? That would be one way to go with that. And the other way would be to look at the energy functional itself. We have a functional with a Dirichlet integral to minimize. And what do we know? Of course, you know already something about what are conditions for the existence of minima or minimizers in the finite dimensional situation, I hope. But now we are in infinite dimensional spaces, and we have to have similar results and considerations. So it will go a little bit in the direction, if we have in finite dimensions or in one dimension, if we have a convex functional, we can be sure that we have a minimum, or a strict convex function, we have a unique minimum. We try to generalize these notions to not only to multi-dimensions, but also to the infinite dimensional situation. So that is something here. And then finally, the application will be nonlinear elasticity. And if time permits, I'm not so 100% sure about that, then number 5, but this is maybe something we can only do very shortly. These are then so-called free boundary value problems. So these are problems of the type. They basically appear, for example, in phase transition problems, where you say, I have a boundary value problem or initial boundary value problem in the time-dependent case, but a part of my boundary is unknown. It's part of the solution to find, and I have a second boundary condition to cope with that. So typical examples will be models for phase transition between liquid and solid, for example, where this separation line or hypersurface between the solid and the liquid part is a priori unknown. So for the last part, if we ever will come to that, I will go back to the modeling book by Harald Garke, Christoph Eck, and me. But these more strictly analysis-oriented parts, as said, I will orient myself, at least in the notation, to the book of Ben Schweitzer, because that's the only book which I know which really covers everything in one book. But we will also give you other textbooks where you have to switch the textbook, so to speak, from chapter to chapter. You can do this, but it's basically very standard stuff. So we start with what we will do now in section 1 is what is called the energy method for the heat equation. So first of all, we start with the heat equation. So with this very simple equation, so let me write it down. So we have an unknown variable u. We have the heat equation, time derivative of u minus Laplacian of u equals, and now we do it as simple as we can do it. We make it homogeneous. We have this in the space-time cylinder. So omega is a bounded set. So typically at least bounded and open, but it has a little bit, we need from time to time a little bit more property, and connected we need a little bit more properties, and then we have this time interval. So all our variables are dependent, and let's see in which direction we write that. We will see that later on. We have always an x and a t as the independent variables. X gathers all the spatial coordinates, so x is has two components, 3 components, and so on. And then in addition we have this simple time interval. So, and as I said, I will use exactly the same notation as and numbering as we have it in the book of Schweitzer. And of course we need a little bit of boundary and initial conditions, and we do it here again, very simple. We take Dirichlet boundary condition, homogeneous, so on the time mantle of this cylinder, and then of course that at least something is happening, we need an inhomogeneous initial condition, so we need something like u equals u0 for t equal to 0 x from omega. So that would be an informal notation of the first equation we are starting with. Of course, you can now say, why do we do that? We have dealt already with this problem. We know what the solution is. We can give the solution at least even in a, let's say, explicit form. As we know, there's the fundamental solution, in some sense the solution for the heat equation with a Dirac distribution at the point x equals 0, t equals 0, and by convolution of this solution with the initial condition, we can get a solution of this problem. This is what we did already. Why we are not satisfied with that? Because this approach or this knowledge, as nice as it is, cannot be extended. It's really, we are stuck to the heat equation. So what we would like to do is, we want to have here a more general equation. We want to have here a general elliptic operator with, say, at least space-dependent coefficients, and then we cannot write down then we can maybe infer that there is a fundamental solution, but we cannot write down it anymore in the way we could do it up till now. So what else can we do? What else have we done? So up to now, representation with fundamental solution. The question is, can this be generalized? We have done something different, which is in some sense not so bad. Also, it's a classical procedure. We have done separation of variables. Remember what this was, separation of variables? It was an approach where we said the solution depends, we have a special form of a solution. It is a product of a function only depending on time and only depending on space. We plug it in and see what comes out, what will come out. And what came out is that those space functions have to be eigenfunctions for the underlying elliptic problem. That would be this here. That would be the underlying elliptic problem. And then, of course, the question again is, can we write those down? And that depends. So this is now the elliptic, would be the elliptic problem. And if the domain is very simple, in one space dimension on a rectangle and so on, we can even write down those eigenfunctions and compute explicitly the eigenvalues. In the general case, we can infer what nature the eigenvalues have. They always are countably many, they are positive, and they have an accumulation point at infinity only. So we have a minimal value from which, minimal possible value from which we start. So this we can infer in general. And then what are our approximate solutions? So and then what we actually do is we set up approximate solutions. Not solutions of the full problem, but only functions which approximate the problem. And the approximate solution, un, let's say, could be here something like, how would it look like? It would be something like, we look at the sum of the n eigenfunctions, so vi of x, this would be the eigenfunction. And then we know how the total solution of this with this component in space behaves. Namely, then we reduce the whole thing to an ordinary to the most simple ordinary differential equation, namely time derivative of the function plus the eigenvalue time the function is 0. So the solution in time is a decreasing, if the lambdas are positive, a decreasing exponential. So we have here something like e to the minus lambda I t. So, and now we have still to fit with the initial data. So here what would be the initial data? If we now plug in t equal to 0, we would have just the sum of the eigenfunctions. That would, in general, is not the initial data. So what we still here need are some coefficients. And these are the Fourier coefficients. The first n Fourier coefficients of u0. And only if we, in some sense, here make an infinity out of this n, then we would have the solution. But then all the questions comes up, in which sense does this converge, and so on and so on. But what we can maybe keep in mind here, that what we are doing here is we are first finding approximate solutions, and then we have not worked this out, and we will also not work this out, this procedure in total. Then we have to deal with the questions, how do these approximate solutions converge? And is this limit which comes up, in which sense is this limit then a solution of our problem? So this could be a procedure to do this in general. So the procedure will be we approximate the problem, such that we come back in the approximation problem to something which we can solve. So what can we solve? We can solve linear ordinary differential equations, here even explicitly. That's the way we did it here. That is what is then called the spectral methods, and you can even make a numerical method out of that. So what this means, we approximate the problem in space and keep it in time as it is, and solve these problems which are approximated in space continuously in time. This gives us our approximate solutions, and then we have to see that those approximate solutions converge, and in which sense. So, but that is a procedure we will do then later on for the wave equation. One could do it in the spectral form. One could also do it in a more numerical inclined form and say, okay, what I do is I discretize in space, for example, with the finite element method, and leave the time as it is. By this discretization in space, I then get an here also linear, because we start with a linear problem, in general nonlinear system of ordinary differential equations. I have to know that I can solve those, and then I have to see how this limit in the n, which then is the number of nodes or the degrees of freedom in the discretization, works. So that would be the approach: discretize in space, leave the time to get the approximate solution. What we will do here is the other way. So here what we did here is, as I said, approximate in space, continuous in time. And this leads us to ODEs, systems of ODEs. So here the alternative, which we now proceed for the heat equation, the alternative is just the other way around. Discretize in time, continuous in space. So what we always are doing, are using here, that these are not just n plus 1 or k or d plus 1 variables, that there's a strict distinction between the spatial variables and the time. They have totally different physical meanings. So what does that mean? What kind of problems do we get here? So maybe we do this first. To get a glance, let me first do this to get a glance, and then we will do a little bit of technicalities before we come back to that. Let me first write down the discretization, that we see it as it is. So what we will do, what does that mean, discretizing in time? So what we do is we have a set of discrete values in time. Of course, we start with t0, and then we have t1, t2. They may be equidistant, but it's not really necessary. And then finally, we have the final one, that is t capital N. So the number, so n plus 1 is the number of our discretization points in time, and that is the capital T. So okay, we make it we could leave it in this general form, but we make it equidistant. For the analysis consideration, there's no restriction. If you really do this as a numerical method, and actually it is a numerical method, then it would make quite some sense to do different time steps. So equidistant means that the tk's are just k times delta t, and the delta t then of course is the capital T divided by n. So we have these time steps in the time interval, and what we then do is we substitute the time derivative which we have. So we have approximate solutions, or we're looking for approximate solutions which only live at these time levels. So we look for uk. These are functions of x. I leave it first informal, not specifying any spaces. And what do we want to have? We want to have a time derivative. Okay, we have something discrete. We cannot write down a time derivative, but we can write down a difference quotient. So the time derivative is substituted by the difference quotient. And now it depends from which side you look at that. If you look from uk, you are so at the interval going from tk to tk plus 1. That would be the forward difference quotient here. And now we have to decide where to take our spatial part. And a possibility, also numerically not the too bad possibility, is to say we take it at the end of the interval. Okay, why is this now? What is this now? Of course, this is now in omega, and we have our boundary value, boundary prescriptions as we have it. So here we inherit the Dirichlet conditions, and what do we have here now for the uk? So now we can argue in the following way. So at t equals to 0, so for k equals to 0, we know the solution given by the initial data. So u0 is just the given initial data. So if we are now at some time level, going from tk to tk plus 1, where we already know the uk, so this is now known in every step, then we have to have here a problem for the uk plus 1. But what is this? This is just an elliptic boundary value problem. And it consists of the Laplacian and a derivative-free part, a zero-order part, with a positive factor. And you might remember that this situation, so to speak, makes the coercivity even better. So if we only have the Laplacian, we depend on the boundary condition really to make a coercive problem out of that. So we need Poincaré's lemma. But with this part here, in addition, we don't need that. So you see, this is just an example. There's much more generality here behind that. Yeah?
Why do we want to have vk equal to 0 and not vk plus 1? Wasn't it that
Sorry. That's a miswriting. That is, so this is the unknown. This is the unknown, of course, and for this unknown we need an... We could ask, so what is this? You might have seen this, or if you do now the second part of numerics of PDE, you will see this very quickly. This is what is called the implicit Euler method. So it's actually a numerical method. Euler, of course, had no computer when he invented it. I'm not sure for which reason he used it, whether he really used it to compute solutions or whatever. But nowadays, this is one of the basic methods. One could do different things here, which are numerically better. There's, for example, the so-called Crank-Nicholson method, where we do here the convex combination of both values. We could, as we now only want to do analysis, the efficiency of our method is not the point. We only, at the end of the day, we need convergence. We don't need a specific rate of convergence. But there are also, of course, a lot of other arguments why the implicit Euler method is nevertheless a good method. Also, we take here a one-sided difference quotient, which means that the order of this approximation is not very good. But that is not the point here. Okay, so let's keep this in mind. What does that mean? If looking at this specific example, it means that what we are doing is we are substituting by this time discretization. We substitute our system by a system of elliptic boundary value problems, for which we know there is a solution and which properties that this solution has. So we'll rely on Lax-Milgram and those things. So the procedure, and of course this is a procedure which we can always, so to speak, iterate. Let's assume we can do this kind of problem at the end of the day. Then we will see, then this is not the end of the story, then we can do all kinds of inhomogeneous data. We can do other boundary values. And of course, then we can also ask ourselves, what about nonlinear problems? Then we can do a similar approximation for nonlinear problems. For example, if we have a nonlinear problem where, for example, here the diffusion coefficient depends on the U. That would be one possibility. Or the heat conduction coefficient depends on the temperature. And we could say we make an iteration. I'm not saying that this is now good to do, but it's a principal approach. Make an iteration. And the iteration, we just start with an initial iterate. Then we put this initial iterate in this nonlinearity, so to speak. We freeze the nonlinearity. And then we get a linear parabolic problem. But this level we have already, solutions of linear parabolic problems. And then we know there's a solutions, we get a sequence of approximate solutions, and maybe we can conclude that there's convergence and so on. So there's always an ongoing story. We can always go level by approximating in each step more complicated problems. Okay. So before starting with that, we will have a look a little bit, what gives us, so this is no problem to write down this procedure, and we know for each step these functions uk exist. Then we can make functions, what we will then do in time out of that. For example, we can connect those values linearly in time, or we can just take it piecewise constant on these time intervals. That would be two simple possibilities. Then we have sequences of functions in space and time. But how do we now conclude that we have convergence, and in which sense convergence of at least a subsequence? And how can we see then what this limit is? And here we have to go a little bit in all this problem of compactness in infinite dimensional spaces. If we would be in a finite dimensional space, everything would be easy. If in a finite dimensional space we know every bounded closed set, so basically every ball in a finite dimensional space is compact, meaning if I have a sequence which is bounded, I know there is a convergent subsequence. And I don't have to think about different notions of convergence, because I know all norms, for example, are equivalent on finite dimension spaces. In infinite dimension spaces, this is different. And in general, we will never get something like a compactness in a norm space. Sometimes one can do this. You will maybe remember the theorem of Ascoli, which basically gives a characterization of compact sets in the space of continuous functions with a maximum norm. So that would be a possibility. We show that the conditions of the Ascoli theorem hold true, and then we know the set is compact there. Then we can extract a sequence which is strongly convergent, as one also says. This will play a big role if nonlinearities will come in play. As long as we don't have nonlinearities, as here, we can be satisfied with weak convergence. So how is this, for example, in L2? If we can show that a function is a sequence of functions is bounded in L2, we know there is a subsequence which converges weakly in L2. And the same thing with H1, or in general with every Hilbert space. So we have to have a notion of solution for which it is sufficient that we have weak convergence, such that we can identify the limit then as a solution of the problem. But this we will do. We'll look at weak solutions. So we have to know a little bit about, for example, compactness properties of those spaces. But what are the spaces? Let's have a little bit of an interlude. I will not make this in all details, but only to indicate a little bit. Before doing this interlude, again, let me conclude this line of thought. So we need boundedness. Boundedness results, a priori bounds, as they are called. And from those we can then, with weak convergence properties, we can conclude, we can go on. Yeah, what kind of boundedness can we get here from the heat equation? So what is the energy method for the heat equation? So the idea is, and later on this will be even easier, you know all this already. So what we do is, we take the heat equation. So again, energy method. Formally. Formally means that we say we have something like a classical solution. Everything what we are doing is okay, and let's see what kind of formulas we get out. And later on we will see how to justify those formulas in a more general setting. So what would we do? We take our equation, put everything to one side. So this is just 0, what I've written down here. Now we integrate in space, and we integrate in time over the interval from 0 to some instance of time, small t. And now we do this. The same thing is true when we multiply here with any function, and we don't take any function, we just take the solution. So this is the ansatz. And later on, it's the same thing as if we would have a weak formulation and taking as a test function the solution itself, what we already did. So now what can we do? The second part is clear. This is just here partial integration, no boundary terms because of the initial boundary. So what we get here in space and time is, so to speak, the Dirichlet integral, so gradient of u times gradient of u, so this term here. This calls for the weak formulation because that's what we did here, doing partial integration to come to this form. What do we do with the first part? And now, if this all is classically okay, then we have a time derivative of function times u. But the chain rule tells us that's the same thing as 1/2 the time derivative of u square. So this is the 1/2 the time derivative of u square, and then we can, space integral is still there, but the time integral, we can interchange these, we can integrate out. So we get here 1/2. I write it maybe first explicitly. Yeah, u square minus, this is a plus, sorry, minus, and this I bring to the other side, minus the same thing at t equals 0. So we have here this term. So what do we have? Here we have our data, the only data in the problem, which is just the L2 norm of the initial data squared. And what do? We can estimate, as even an identity, a so-called energy identity, we can estimate the same term for arbitrary instance of time by this term here. So here we have now u evaluated at t, so the spatial function, if we fix the t, also in L2 squared. And here we have this additional time-space term. This at least is greater or equal to 0. That means this term is always less or equal than this term. So in terms of the data, we have here an a priori bound. And in which space is this a priori bound? It is spatially in L2, but in time we have every instance of time estimated. This is pointwise. So we have L infinity in time. So what we have here is an a priori bound. What we see here is an a priori bound, and we expect, that means we expect solutions. No, we expect solutions, let me write it down, in those norms which we can bound, which we can control by the data. And what is this? This is L infinity in space. In time. What did we have? L2 in space. And in additionally, what we saw here, this is L2, so to speak. This is L2 in time. And now we have here the L2 norm of the gradient, but we are in the Dirichlet situation. With the gradient, we can also control the L2 norm of the function itself in space. So we have the full H1 norm here. So we have here H1, or more precisely H10 of omega. So now I've used already a new notation for spaces. And I hope you have some feeling what they mean, they're supposed to mean. But there are, in fact, they are new function spaces, what we have here. What is new here with these spaces? These are spaces on the one hand side, they are quite simple spaces because they are only on an interval in time. And here they are L2, LP, L infinity spaces, or later on W1 spaces, so spaces we know. But what is new with these spaces is their values are not in the reals, they have values in a Banach space. So we interpret this xt or tx function now as a function in time with values in a Banach space to cope with this x dependence. So how do these spaces relate to each other? In principle, one can avoid this notation because there is and a sort of so these spaces are called Bochner spaces. Bochner space means you have some LP or Sobolev space on a time interval with values in a Banach space. So I will not dwell too much on the Bochner space. We could now do all this theory, and this would keep us busy the next 4 weeks or so. I'm not saying that's uninteresting, but that should not be the focus here. Let's frame it in this way. We can avoid Bochner spaces. In the sense that we write them down in a way that we don't formulate it as in this form here, but we formulate function spaces more classically on the space-time cylinder omega t. So, for example, the most simple Bochner space is, of course, this one here, L2, L2. Of course, this is supposed to be the same thing we would expect as just being the L2 space on space-time. And what else do we have seen? We have seen, for example, L2 H1. And here we would say this should be something like those L2 functions. So those L2 functions on the space-time cylinder. Maybe I now abbreviate this also with Q or QT, such that what do we want to have? We want to have that the gradient, and now we have to be, as we have the x and the t derivative, we always have to make sure that it's clear what we mean, that therefore an x here is not bad to write, that the spatial gradient is again an L2 function. Now let's use the abbreviation. So, and okay, another way to write that. So what we later on will also need is this space here. So what is H minus 1? H minus 1, that was a shorthand notation for the dual space, the topological dual of the H10. So the set of all bounded linear functionals on this space. And so we can use any Banach space here as the image space. Why not using this space? So what we have here is we have here a dual space. We know the L2 space as a Hilbert space is with a natural isomorphism via the scalar product isomorphic to its dual space. So we always identify the L2 with its dual, what we will also do later on. So what we expect here is, so we have a dual and a dual, so what we expect here is something, and that will also turn out that the whole thing is just the dual space of this space here, which we can write down in a non-Bochner fashion similar to this space here. So in principle, we could avoid this Bochner stuff. Nevertheless, it's quite helpful. And let me just summarize a little bit of results which we have for it. First of all, if we start, we have also X is a Banach space. Let's make it general. P is a number between 1 and infinity. And we ask ourselves, what about the space LP0TX? So the first question is, if we would like to speak about integrable functions. So what we want to have here, we would like to have functions whose p-th power is integrable. So first of all, we have to speak about integrability, and for doing that, we have to speak about measurability of functions with values in Bochner spaces. But this is very analogous to the Lebesgue theory, which you hopefully know. How does one do it in the Lebesgue theory? Opposite to the Riemann integration theory, one approximates the functions by what is called a simple function, a function which only takes up a finite number of values. So we have quite a simple image space, and the pre-image is then subdivided in those subsets which are mapped to these finitely many values. So for such a simple function, we can, for example, write down what the integral is. This is a sort of a general step function. So we just take the value times the measure. So at 0t, we take the Lebesgue measure, f0t, times the measure of this subset, and then we sum up over those values. You should know this, at least if you know a little bit of probability theory. That's a discrete measure, or whatever. So now we ask, and then the next natural step is we take the limits of those functions. That would lead to the notion of strong measurability. But now, as we are here with these infinite dimensional spaces, there is a theorem of Pettis, and I only phrase it because we will not use it more in detail. It basically says this notion of Lebesgue measurability, this notion of strong measurability, which we have just defined by this limit process, is the same as if we do the following. We take a function from this space, put a general element of x prime on it, a general linear bounded function, and then in this composition we are again now in the reals, and if this function is now in the usual Lebesgue sense measurable for all possible elements of x prime, then it's exactly the same notion. But that this holds true needs the separability of x. So again, what means separable? So we have Hilbert spaces, that's clear. These are spaces which are where the norm is induced by a scalar product, and which gives us, via the Ries representation theorem, a natural isomorphism between x and x prime. And of course, having this between x and x prime, we also have one between x and x double prime. But on the other hand, in general, what we always have is a natural embedding of x to x double prime. By just how is this element of x double prime defined? Take its arguments, so an element of x prime, and evaluate this element at the given element of x. So to speak, the point function at x prime. This usually is an embedding and not an isomorphism. If we have it as an isomorphism, then we call this space reflexive. So the LP spaces for P having this, we can always go back and forth because that means it doesn't make a difference whether we view a space as a, so to speak, original space or as a dual space. If we look at an LP with a P strictly between 1 and infinity, then only for P equal to 2 we have this identification with which is dual space. In the other case, we have an LQ such that 1 over P plus 1 over Q is 1. But now, again, taking the dual, we are back to the LP. So in this sense, we always can go back and forth between dual and non-dual space in the reflexive situation. The non-reflexive situation is much more complicated. So the dual of the L1 is L infinity but the dual of the L infinity is something more complicated. I hope. I haven't looked at functional analysis for quite some years, so hopefully I still am able to do it. Okay, so what we usually will assume is reflexibility. So that's not this. We can work with all LP spaces. So what I've said now in words, and I'm not going to write down, gives us now a definition of this space. That just means that it's this space where the P's. So how is the norm defined here of this space? So what we do is we take the norm function. So they substitute, so to speak, the modulus in the scalar situation or in the vectorial situation. We take the P's power, and then this integral, this Lebesgue integral, is supposed, which exists as an element of either R or infinity, is supposed to be finite. That selects those functions which we have here. So this is the definition. To be finite is the definition of being an element from the space, and that is then the norm we have on this space, and this is then a Banach space. Okay. There's a basic theorem of Bochner. I'm not sure whether I'm now going to write it at the blackboard. Maybe only a few ingredients from it. Not everything. That we have some working knowledge of these functions. So, one important thing is the following estimate we would like to have, and we have it. So, on the one hand side, we have this integral. This integral is an element of X, of the Banach space here. And on the other hand, what we can also write down is, we can look at this function here. We should be a t, of course. We look at this function here. This is now a scalar function. We could also ask ourselves about the integral. And what we would like, what we expect from our knowledge, if this is a scalar or a vector in Rn, we would expect something like this here. And this holds true. So we can always work with this estimate. And the same thing is, if lambda is, here it's called lambda for some reason. Why lambda? Yeah. If we take in lambda, okay, I said I stick to this notation. Lambda from x prime, a dual element. And then I can do both things. I can look at the integral, which is an element of x, and I can put this into the lambda, so I can take the dual pairing between the lambda and this element of x. So this just means apply the lambda to this element of x. And that is again the same as if we can, so to speak, put this through. We put the lambda at all the UTs. Now we have scalars, and now we do the integral. Should not write the x here always. So these are maybe the most important things how we can work to this, and there are further things which basically say the theorem of the Lebesgue theorem of majorized convergence. So I have a converging situation and I have a dominating integrable function, and then as a consequence, the convergence is not only pointwise, but it's also in the integral, in the L1, in the LP sense. This also holds true here. So one tool we try to avoid this. One tool to deal with those in general. How does one work with such general functions which are not so regular? We also did this to some extent. For example, did we do this? Look at the oh God, my English. At the trace theorem, did we look at the proof of the trace theorem? I'm not sure. Okay, one way to do is that one first works with smooth functions, proves these estimates which one has in mind for smooth functions, of course avoiding all these, in the final result, avoiding all these higher order derivatives which one would have due to the smooth functions, and then do some density argument saying, okay, these smooth functions are dense in these norms which appear here, and then I can go to a limit and have it for all the functions. And a more explicit way to do that is to approximate a special a function from these general spaces by a sequence of smooth functions by doing a convolution with a special function. And that is a tool to deal with that. That is a tool we would need if we would like to prove all these things. But I said we will restrict ourselves a little bit only to have a look at the results. So the next question is, what about the dual space? And the assumption again is now, from now on, as I said, X is reflexive. We have a P between 0 and infinity. 1 and infinity, so 1 and infinity is excluded, and we have the conjugate of it, so we have a Q such that 1 over P plus 1 over Q is 1. And now we can say something about the dual space here, about this thing here, and this is, when I say it is, I always mean it's isomorphic too. It's isomorphic too, so maybe it's better to write it like that. So if we would have here scalars, then we would know what the dual space is. The dual space would then be LQ, as I said. And now, okay, as we saw it already in the example here, in the last line, what you would expect and what actually is true is that here in the image space we have the dual of the X. So it's quite formal. We just put the prime forming the dual here and here. Okay. So what does that mean? What does this identity means? It means that if we have an element U from LP, and we have an element, let's say V from, is it V? Yeah, from LQ, then okay, I would write it the other way around. Okay. Sometimes I'm in conflict with the book, but I said I stick to the book. So I keep the formulation here of the book. So the formulation is, it's UV. So this can now mean several things. It can first mean the following. It's something like a generalized scalar product. So if this would be 2 and 2, then we would have here the scalar product. And it's similar as in the real valued function. Now we have here in the interior the scalar product of the. Let me first write it down. Okay, let's do it in several steps. Okay, let's assume the X is a Banach, is a Hilbert space. then we would say, okay, we can write this down, and this is just the scalar product of the Hilbert space. And that would be, so to speak, an obvious scalar product then of L2, 0t, x being in Hilbert space. Now, if x is not in Hilbert space, but only a Banach space, here reflexive space, then we have here in the same notation, or in a similar notation, the dual pairing. Then we have the dual element applied to the element of the space. And here I would write it the other way around, but here the dual element is written here to the right, anyhow. Okay. So, and in this sense, what we here define is now, so this makes sense, what is written here, and this defines just a bilinear form here, again, on our spaces. And it's this bilinear form which, so to speak, is the dual pairing, which gives the relationship between an element of the dual space and an element here. So the assertion is, if I have any element of the dual space, for this element there is a unique V from LQ and so on, such that applying this dual element to an element U is given by this. And in this sense, this is now the dual pairing between these two norms. So dual pairing just means application of the dual element to the element of the space. And basically, it's quite often it's an extension of an underlying scalar product. So now, up till now, we had no time derivatives. Of course, we also need time derivatives. So the next space which we need with time derivatives is so we need a time derivative. And a time derivative, so if u is from LP0t x, then we need a distributional time derivative. Why it's so important always to refer to the distributional derivatives? We will encounter the situation that we will have derivatives in different senses. For example, classical derivatives, weak derivatives, whatsoever. And we want to identify them. And we need, so to speak, a third common relational point, which is always more general than the other ones. And the most general version is the distributional derivative. And on the other hand side, the distributional derivative fulfilled, it's unique. So it's something, if A is the distributional and B is the distributional derivative, then they are both the same. And it fulfills all the rules which we know about derivatives, because distributional derivative only means put everything to the test function. And so this we do here too. So we just say, what do we have? So the time derivative of u, and to indicate that this is a distribution, is this with these brackets. So if only one argument, so this is different from this here with two arguments. If only one argument appears, it means that's not really a function, but it's a distribution. And we need our very smooth test functions for the distribution, so the C infinity functions, with a compact support on the interval 0t. And now the things become simpler, because now here we can rely only on reals. We don't need here something with x prime or so. And so what do we do? How is this functional defined? Let's say for an element phi from this, what do? We integrate in time between the derivative, which we do not have, and the test function phi, and put the derivative, let's say in parentheses, by partial integration to the other side. So it's defined by this function minus ut time derivative of the phi. So it's basically the same notion of distributional derivative, what we know already. So, and then, quite similar to the classical Sobolev spaces, we say, okay, we are not satisfied that this is just a distribution, just a functional. We want to have a function representing this distributional derivative. And if we look at the space, for example, at the space W1P, 0t, up till now that would be, so to speak, the classical Sobolev space, but now we have it x-valued. What do we want to have here? We want to have two norms. What do we want to have? We want to have that the function is in LP, of course, 0tx, and it should be, and the time derivative. The time derivative in this sense here should also be a function, should be represented by a function, and this function now is supposed also to be in LP 0tx. And then, of course, we have the corresponding norm. And the norm now in this space, the norm in this space now is, and in this is a norm, it is a Banach space. The norm is, we have to take just the norms of these two ingredients. And here it is defined, and therefore I will stick also this definition. It's just that we add up these two norms. Maybe you find this now at the first glance a little bit irritating, because up till now what we did, for example, for p equal to 2, what we did, we took the square of this and the square of this and took the square root out of the sum. But you can see it in the following way. What we have is we have a tuple, here a 2 tuple of this number and this number. And to make a norm out of that, we need a norm at the R2. But which norm we take is absolutely unimportant. Of course, it changes the number, but all those norms are equivalent. Of course, we could also here take a power p and here power p, add up and take the p's root. Would be an absolutely equivalent norm. So why make it complicated if you can make it easy? But of course, this also applies already to Sobolev spaces, but there's more traditional really to take this other form, other equivalent form of the norm. Okay. That's again now a Banach space. All these spaces, so we never will lose this property. From time to time, if we start with a Banach space, and from time to time to have the properties we would like to have, we need the reflexibility in addition. So for reflexible X spaces, everything is okay. Okay, so trace. The trace is here much more simpler than in the spatial situation, because we just have an interval. And trace means we want to evaluate a function at one point of this interval. If we would have a continuous function, then it would be obvious. Then a continuous function we can evaluate. Maybe we come to that later on. We can first clean the blackboard. So why do we need, for which ingredients of the problem we need the fact, we need something like a trace, or we need something like continuity in time, which would not make sense, or which would be, it's unclear, which part of the, so we have three parts in our problem. Here you can have a last look at it, at these three parts. For which of these three parts we need this trace property? You see this? Last chance before I erase it.
For the boundary, because that's where we want the function to be 0.
Yeah, but that's a trace in space, and that is, so to speak, already integrated in the space x. If we say x is h10, then this is already integrated. It's for the initial data. Because in time, what we have to have a notion that in time it makes sense to say at t equal to 0 there is some condition. Of course, if this only is an L2 function in time, that doesn't make sense. So we need trace notions, and finally we need continuity in time in our notion of solution. But nevertheless, I think it was good that you mentioned this, even if it was not correct, but because it tells everything that is the advantage of this approach. Everything what is concerned in space is already encoded in the x. That is strictly separated here. Okay, so wo sind wir jetzt? So let's just put down this notion of trace. So we have an element. We cannot do this for an L2 or LP function. Of course, why should it be easier having an X as an image space a part of R? So we need more. We need some weak derivatives to have this trace. And this is enough to have this W1P. So, and this P, I have not specified that, but I think the P can include the 1 here. So this P is between 1 and infinity. So what about now the trace? Let's do a computation which would be obvious if we could evaluate the function. So let's say we start again with a term like that. So to speak, with a up to the sign, with a distributional derivative. So we will later on specify what the phi is. And now we do partial integration. So we put the whole thing onto the other side. And now we don't want to have it in general at t at 0, but at t0. So we go from t0 to t. Partial integration, now we have the derivative here. And this we can do because this is now an x-valued LP function. It makes sense. And we have here, so what is this? This depends, of course, on what we have on the phi. If the phi has compact support in the full interval, that's just 0. That's just a distributional derivative. Now we are a little bit more, if we have no restriction on the support, then we would get the boundary terms. So what we only want to get, we want to get one boundary term. So what we do here, we take those test functions here, very smooth, compact support, but now there comes the difference. Here the T0 is included here. So the compact support can go up to the T0, but it is beyond the capital T. So we have here no contribution from the T0, but we have here a contribution no contribution from the capital T, but the contribution from the T0. So if this, now we turn everything around and say if this identity holds, then we call U0. So U0 would be something like, in classical terms, U of T0. Then we call U0 the trace of the function at this point. So and the notation is, do we have a notation for that? Is something like, okay. So from this now we can conclude the fundamental theorems. Do you know the fundamental theorem of calculus, of course? And now we have also the fundamental, so to speak, the fundamental theorem of calculus for Bochner functions. So what does that mean? What we would like to do is we would like to integrate the derivative, and we would like to get, so what we would like to have is we have two numbers in the interval t1 and a t2. We select two numbers. We would like to integrate from t1 to t2 over the derivative. This is then formula 1017. Like integrate over the derivative, and in classical sense, scalar valued, and for continuously differentiable functions, of course, this is then, of course, ut2 minus ut1. And this also holds true here with a very slight exception, namely, the exception is for almost all. So up to a set of measures 0 of points t1 and t2, this identity holds true. In this context of the W1P functions. So to turn the thing here around here, to turn this identity around, we can now define the trace. We can define the trace. In the book it's Spur. Spur is the German word for trace. The trace at T0 is now a mapping from 1 P0T x to x. This is still here an element of x here, of course. And what do? We just take this identity here, and we have to restrict ourselves a little bit with a phi. So this value has to go away, so we have to take here the test functions with phi at T0 equals 1. So the trace is just, so we map u to, now we have the minus, we bring the minus to the other side, to minus T0t, ut time derivative here, and keep it in the integral, and here then the time derivative on the other side. So all these terms make sense. And now the test function is the same as above. The T0 can be touched, or has to be possible to touch, the T, capital T not. And now we need to have phi of T0 equals to 1. We scale them to 1 there. Or otherwise, we could also take a general one and subdivide here by phi of T0, of course. Okay. And what holds true is, here in this case, maybe I put it here, for this kind of functions we have, this has to do with the fundamental theorem, we have ut equals trace of, how to write this with a t, yeah, I have to write it like that. Trace of u at t for almost all t. So up to a set of measure 0, this is really, this is the value which we have, but at a set of measure 0 we might get the wrong value. And only in the situation when we have a continuous function, then in the case of a continuous function, we can, so to speak, select this continuous representative, and then this almost everywhere goes away. So that would be, which we think we cannot do it completely today. That would be the next step, which is first a simple step, namely to do the same thing not for LP functions, but for continuous functions. So you have here something like C, 0tx, continuous functions on the interval with values in x. And then the next step is an embedding theorem. Is it possible to get, if we know something about the function in LP, if we know something about the derivative in LP, do we then know more about the function with respect to continuity? And this will hold true, and this will be then maybe the final things which we then will need. And having that, then we can go back to the energy estimate. And what we will then do next time largely is to not then deal with this, what is now not on the blackboard anymore, to deal with these time discrete approximate solutions given by the implicit Euler method. So what we have to do is we have to derive a priori estimates, see which kind of conversions we can conclude, and then we have to see what we can conclude for the limits. And in this way come to an existence proof. Okay, this we will then do next week.